All right, welcome my friends to this month's first Friday at Fusion Studio. My name is Rich Dione. I'm the co-director of the Fusion Studio for Entertainment and Engineering here at Purdue University. With me is my colleague and best bud of all time, Mary Pilat.
Co-director of the Fusion Studio. Thanks for joining us today.
Yes, and we're super thrilled to have with us today Ben Gasper and Adam Piotrowski. I hope I said your last name right, Adam. I meant to ask you the pronunciation, so it sounds like I got it. They're here from TAIT to talk about control systems and automation that they work on. Really thrilled to have them here. I'm not going to do much more of an introduction because time is of the essence. So Ben, I'm going to turn it over to you to sort of take us into this, and we'll go from there.
Yeah, hi, my name's Ben. I am the technical sales manager for North America for TAIT. I've held a number of hats at TAIT before in my 10-year tenure. I was a integrator, I was a project manager, and then before I came on to the sales team, and now I exist on the sales team to help the rest of our sales team members really kind of dive into the technology and the software and control systems and rigging and mechanical systems as needed with clients and future projects. Adam, would you want to care to do a little introduction of yourself there?
Yeah, good morning / afternoon, depending on where you are in the world. My name is Adam Piotrowski, as Rich mentioned. I'm a senior control system designer with TAIT. What that means is I look after project level designs, as well as some of the nitty gritty when it comes to cabinet and enclosure designs. So we will go through a host of acronyms and the different components of the system when it comes to selecting, specifying, and interacting with all groups of both the TAIT company as well as contractors that we may require when we do our projects. Like Ben, I've worn a couple different hats over my years with TAIT, from integration to support, and a couple times in design, and it's always brought me back. So here today to talk and share is whatever I can. And I think, as Rich had mentioned, we're able to take questions, so feel free as we go through this, post them in the chat, and we'll try to get to as many as we can, and again, share as much information as we can.
Awesome, thanks. So how do you all want to start? Do you want to just jump in, Adam, or is there more introduction you want to do?
No, I'm good to jump in if Ben will let me do it.
I'll let you do it, Adam, right? Like I have any control. Yeah, let's jump right in and take a look at what Adam's got here.
Excellent. So again, Ben and I are both with TAIT. TAIT is an entertainment automation company. We do everything from the big Cirque spectaculars here in Las Vegas to cruise ships to regional theater, professional theater, theme parks, music tour industry. You name it, TAIT probably has something to do with it in the entertainment industry. We're going to go through and we'll, set some foundation to things and talk about the TAIT system specifically, Navigator automation platform, and then we'll get into kind of the overview and what it takes from my, a controls designer, either myself or somebody on the team, when it comes to getting the system together and actually getting it designed and what it takes to put one of these systems together. So we kind of already did the introduction, but again, we're here to talk about the Navigator automation platform. This is the flagship product that TAIT offers and brings to the industry when it comes to both show control and automation control. We'll just do some acronyms and abbreviations. TLAs, everyone's favorite, and you might say, well, what's a TLA? So it wouldn't be appropriate to define the acronym with an acronym. So TLAs, 3-letter acronyms, TAIT loves them. In controls, we deal a lot with electricity. This is both AC, alternating current, as well as DC, direct current. We have a couple different products that we have developed and use in a lot of our systems. So just to talk through a couple of those, ESA is our e-stop appliance. So with an automation system, we're not going to let you move it if you don't have a way to stop it. And so our ESA is our safety master to take care of that. When it comes to like a front end system, you usually have a graphical user interface. I'll usually just refer to it as a GUI, and this is definitely a vital part of any control system to ensure that your operator has a way to gather the information from the system, do any sort of troubleshooting that may be necessary, as well as command the motion and follow along to make sure that axes in the system and the show is progressing as it should through its queue list. IGBTs, I may reference it when I get to drives. So that's insulated gate bipolar transistors, essentially electronic switches. MCC, motor control center. So this is the type of cabinet that the control system designers will end up working through, designing, detailing out, and this is kind of really the heavy lifter when it comes to the piece of equipment that makes a control system a control system. MCR, this is our motion control rack. This is the other half. So if the MCC is doing the heavy lifting and all the power conversion for motors, the MCR is doing the brainiac, or it is the brainiac. It's doing the closed loop positioning. It's storing your cues. It's playing back and sending out all the industrial field bus communications to either the MCCs or any remote I/O that we may have in the system. And then usually in an MCR, we'll have a PLC, a programmable logic controller. So this is, again, an industrial piece of automation hardware that is able to be programmed. You can write your logic in it or do motion control with it to make sure that, again, your axis is on track. We get into some of the I/O level of things. So SSI, it's a synchronous serial interface. It gets used a lot for encoders. VFD, variable frequency drive. And this, again, is one of the components that will be housed in an MCC when it comes to doing motor control. So one of the big things that we have to deal with control system design is I/O. And you may say, like, well, what is I/O? Input and outputs. We generally have two types, digital and analog. And within those types, you have the input side and the output side. So we get a total of 4 combinations. Digital inputs, which could be a normally open and normally closed, but there's usually 2 states. It's either on or it's off, a 1 or a 0. You have digital outputs, you have analog inputs, and you have analog outputs. And together, all of this is kind of really the bread and butter. Sometimes it's done over a network, and you can send a digital bit via network, or you can send a register of values, more like an analog input. Your digital I/O is, again, something that's usually 2 states. It's on or off, a 1 or a 0. And then analog is something that has an infinite range between 2 points. So this could be considered as 0 to 100%, could be 4 to 20 milliamps, plus or minus 10 volts. And so you can essentially infinitely choose with a dial, a slider, a dimmer, however you want to consider it, to be able to pick that value. And that's usually either a set point for a drive or the encoder feedback in terms of where your axis is in its position. So how do we then use this I/O in a system, and what do control system designers have to be aware of to make sure that they accommodate in, be it the MCC or the MCR, when it comes to actually designing these cabinets and putting these systems together? So from a digital input standpoint, we have things like limits, brake check back, e-stop buttons, and your go stop buttons. So limits, from the TAIT standpoint, our machines, we usually end up having 6 sets of limits, 3 on each side. The higher range and the lower range are a plus and minus direction. And one of those limits is purely software based. It lives in the controller, doesn't actually have any switches. So we don't have to worry about that from a digital input standpoint. But then we have the next, moving towards the extreme of travel, we have an initial limit, and then we have an ultimate limit. And those certainly are hard pieces of I/O that we have to make sure we bring into the system and we can evaluate them. Brake checkback is usually used in our safety system to ensure that the brakes are functioning. So brake checkback is more or less a switch, a micro switch that monitors when the brake opens or closes to make sure that it has actually done so as we've asked it to in a very specific time, because that can, a brake taking longer to open or longer to close may indicate a problem, and we want to provide that feedback to the operator to ensure that, you know, the machines are able to be maintained in tip-top shape, especially if we are flying a person around. E-stop buttons, again, as I mentioned, when with that ESA, we're not going to let you move something if you don't have a way to stop it. And e-stop buttons are definitely a vital part of a control system design to ensure a reliable and safe way to stop systems. And then we have our go stop button. So this comes kind of to the GUI and consoles that TAIT provides to make sure that we can initiate motion and stop motion, advance cues, adjust cues, anything like that. Digital outputs. So again, things that we're going to command or control. So like brake coils. So this is the counterpart to that check back on brakes, is we need to tell the brake to actually open. Any kind of indicators or status lights, cue lights, e-stop indicators, things like that. And then something called safe torque off, which ties to that e-stop button when it comes to the VFDs. And that when you hit the big red button on the e-stop, you want to shut down the drive and ensure that there's no way for torque to be generated at the motor. And this is one of our safety functions that gets incorporated into the control system. So jumping over to analog inputs, things like load cell, the position feedback in terms of the encoder, and any kind of jog joysticks. So load cell be used on a winch to confirm the load you're picking up, kind of be used as a scale, but also if, again, safety functions and performer flying, ensuring that that winch or that machine stays within its designed limits. So if it can only lift, 500 pounds, that we don't try to pick something up heavier than 5,000 pounds. Doesn't really have a way of doing that if you don't put a load cell online. Position feedback, very important in a control system. If you want to send something to a position, you got to know where it is. So this can be in a couple different flavors. I had mentioned SSI in the beginning. That is just one of many type of encoder feedback protocols. There's things like NDAT, sine cosine. We'll get into some of the differences later in the slides. And then jog joystick. So if you're not playing back a cue, so if you haven't written your cue, but instead you want to just send something up or down until somebody calls a stop, you need some kind of input for that. And so jogging is the term that we use. So you need a device, whether it's an actual joystick or a pot wheel to be able to get that feedback into the control system. And we have analog outputs. So things like the speed set point setting to the drive. So the control system is doing its loops as I need to be at some position. I need to then tell the drive to move that, and it's going to do that with a speed set point. Other things to consider are, I mentioned it, that normally open versus that normally closed. And so if anybody doesn't know, what is normally open? So normally open is a switch that is normally open when it's not pressed. So it does not provide the voltage to the digital input when it's not pressed. So there's no signal when it's in the idle state, and it must be actuated to signal. So how would we use this in the control system? So this is good for sensors or buttons that initiate motion. So things like an enable button or a go button would be good to utilize a normally open switch. The flip side of that is a normally closed switch. So this is something that does signal when it's in the idle state. And signaling doesn't necessarily mean that it's going to make something move. It's just that the PLC or the input module is going to see that voltage. And so when it's actuated, the signal is removed. And so this is good for safety devices that you want to ensure are in working order before you end up pressing them. And that's because you're able to detect cable breaks when it comes to a normally closed circuit, because it is in its idle state, it does signal. You can check and make sure, is is it still there? Does it still exist? So this is good for limits and buttons that you want to stop motion, so that if the cable was to break, or somebody was to run it over with a forklift, or it was to get, it's on a moving lift and it gets severed by a shear edge, if that limit goes away, the control system is absolutely going to want to stop, because if the machine then extends past its normal motion envelope, if that limit doesn't exist anymore, you have no way of stopping it. And then there's kind of a mix between these two, which is a changeover contact. It's a little bit of both. You can have it both as a normally closed and a normally open, and it flip-flop between the two. And then we get into encoders. And so I mentioned some different protocols of different encoders, but before that, we're just going to talk fundamentally about the different type of encoders. So we have this incremental encoder, and we have an absolute encoder. And again, for anybody that doesn't know, incremental really doesn't have a position. You turn it on and it says, I have moved plus or minus from the time I have been powered on. It doesn't have a reference to where it is in its range of motion. The counterpart to that is an absolute encoder, where it does have discrete, unique disks or discrete positions in a single revolution of rotation, but you can also have things called multi-turn encoders that are able to detect not only its position within a rotation, but how many rotations it has occurred. And whether you turn it on, spin it by hand, or turn it off and spin it by hand, you'll be able to detect that anytime it powers up to know exactly where it is. Whereas with an incremental encoder, you don't. But there's some pros and cons to both of those. Incremental encoders are cheap. And so one of the tasks that we are given as control system designers is to ensure that the system is as value rich as possible. So we don't want to bloat it with a bunch of extra sensors or features that the client isn't going to ultimately use or would never use, just because maybe they're not at that level when it comes to like a spectacular out here in Las Vegas versus a regional theater that really just needs the main curtain to go up and down. So absolute encoders, thus be a bit more expensive. Incremental encoders are simple. They're usually just a single disk of tracks, where an absolute encoder has more complexity to it. So incrementals are only able to know their direction and counts moved from a power up, where you can, with an absolute, you are able to know the direction and counts moved, whether it's powered up or powered down. Once it powers up, if it was moved while it's powered down, you know that it did in fact move. You can have multiple protocols for incremental, multiple protocols for absolute. You'll lose position if you're powered down and your position is not stored. So this is something that the control system would have to do. It'd have to essentially, once it completes a move, go, great, I'm going to store that position, so that if a power event was to occur, you wouldn't have to re-zero or re-reference your axis, where an absolute encoder can maintain position during that power cycle. You lose position if manually moved and then not plugged in, or then plugged in, versus knowing the position if manually moved and then plugged in. So again, being able to know where it is in a rotation, absolute being able to know where it is in a rotation and how many rotations it's done, where an incremental only knows from the time it's been powered up. And you can do single turn versus multi-turn. So this is two examples. The top one there is an example of an incremental encoder disk versus an absolute incremental disk. And so incremental is essentially a repeating pattern of dark spots and light spots, and the photo sensor there is able to detect when those different tracks go up, are in the light spot or in the dark spot, and depending on what one happens first, it is able to determine direction, but it just repeats. It's a repeating pattern, whereas that absolute encoder disk on the top right hand side there has very unique individual pieces, and it doesn't repeat until you've done a full 360 degrees. And while that's a bit simple, that bottom picture is 4,096 unique positions. So resolution is something that we look at when we're doing control system design for an encoder to make sure that we are able to get the necessary resolution we need to ensure that the control system is able to get good updates or a good update rate to ensure good closed loop positioning or closed loop control of the axis. And so instead of doing 360 degrees, we can do 4,096 positions over that 360 degrees. So drives, like I mentioned before, drives are in our MCCs and are a vital part of any electromechanical control system. And there are definitely different ways that you can provide motive force. Hydraulic is certainly one of them, but a lot of what TAIT does is in the electromechanical. And so I'm going to focus a bit on that specifically because it definitely relates directly to the control system. And so there are two big pieces that make up a drive system. You'll have an in-feed and rectifiers, and you'll have inverters. So the way that a drive ends up working, or the control system ends up working in order to produce the different voltages and the different frequencies that it needs to spin a motor is by converting that incoming AC from the utility into DC. And so that's done by the rectifier. It's done either by diodes or those isolated gate bridge transistors. It does power filtering, and it may allow for regenerative braking if necessary. Whereas the inverter is going to do the DC to AC conversion. And so this is how you can spin a motor at, half speed, 30 hertz instead of 60 hertz. It's because this inverter is essentially reconfiguring the three-phase voltage that you would get straight from a utility by converting it to DC and then reforming it into AC on the opposite side. And so this device controls the voltage, frequency, and current supplied to the motor in order for us to be able to control speed, control current, and ensure that we can follow our position demand as we are queuing it from the front end to make sure that it's doing what it's supposed to be doing. And so drives can be AC-AC, where the AC to DC and the DC to AC happens all in one unit, or there can be separated units where a drive is just a DC to AC portion. So it's just the inverter stage, and then the AC to DC happens in a rectifier stage. And this is important when it comes to component selection for us. TAIT uses a couple different manufacturers when it comes to drives, as well as PLCs. And depending on the application, we may decide to go with an AC-AC drive, where it's all packaged in one unit, or we may decide that we want to actually break it out into a more modular or scalable system where the drive is actually just the DC-AC stage, and we have to add in an inverter, a rectifier or an in-feed. And so with that, we have the ability to share. And you may say, well, what do you need to share? And it's sharing the DC bus. And so this is a picture of one control system, one MCC specifically that I designed that utilizes DC bus sharing. And why may we opt to do a system that utilizes DC bus sharing? It allows to share regenerative energy before having to rectify more to the utility. So in this cabinet, we have actually 3 drives. So we have these first 2 drives, which are 85 amp drives, followed by a 45 amp drive. And what we're able to do there is if one motor happens to be regenerating energy, moving with gravity, utilizing or converting that potential energy stored in gravity to electrical energy because we're lowering that load, it can push it back to the DC bus. And if one of these other drives is lifting a load, we can essentially reuse that or recycle that energy before we have to pull more from the utility. It's also fairly power dense because we're not duplicating that rectification stage. That rectification stage is only happening once, and that's what these 2 units on the right side is our rectification stage. So we can make the cabinet fairly power dense. And so it's typically made up of one rectifier and then several of those DC to AC inverters. The counterpart to that would be no DC sharing. And so what we have here are two AC drives. And so this does require some additional components needed for the power distribution, but you are able to put everything in one piece of equipment. So you're able to kind of make it very size efficient. So you're able to make the cabinet smaller, and you're able to be a bit more cost effective when you're only looking at single or very low access count MCCs. Field bus is another important part of control system design. We have to make sure that the MCCs are talking to the MCRs, and then the GUIs are talking to the MCRs. And so the field bus could be thought of as the public transportation system for all the IO. If you're going to press your go button, that needs to make its way to the system to start initiating motion. If you press the e-stop, it absolutely has to make its way to the system to make sure the drive shut down and everything stops. I have automatic lights and I'm now in the dark. So we have many different protocols. This allows for real-time distribution of IO, and the manufacturers typically pick one protocol and build their products around it. So some of the protocols that we use here in TAIT are EtherCAT, Profinet, Profibus, and Ethernet IP. Backoff is primarily our EtherCAT manufacturer. Sorry, Backoff is one of our manufacturers that we use for industrial hardware that has really centralized around EtherCAT. Siemens is another industrial hardware manufacturer that we use and can incorporate into our systems, and they have focused and really standardized around the Profinet or Profibus field buses. And then Allen Bradley, another manufacturer, has used Ethernet IP. And so this also becomes a factor when we're doing control system design, because we need to make sure everything can talk. So if we've got a Siemens MCC and a backoff controller, we need to find a way in order to get that EtherCAT communication over to a Profinet type of communication. And so that does exist, but again, that incorporates or starts to add a complexity to the system. We want to make sure we try to keep things as simple as possible to make sure that they can be, troubleshooting is a relatively straightforward process, and any newcomers to the industry or to an installation or a project can be brought up to speed quickly. So again, this is what we use here at TAIT. So I talked about the GUI and the Navigator automation platform. So this is just one image of one of our consoles. This happens to be the Epic console that we use. So this is what the operator would be sitting in front of, and how they interact with the system, how they queue, how they get their feedback, how they execute a show. And while we don't redesign the console for every show as a beginner product, we do need to include it to make sure that there is a way for the operator to write their cues, again, initiate motion, and you'll see the e-stop button in the top left there to stop that motion. So now that we've kind of talked about all the pieces, how do we bring it together? And so I talked about the field bus and the network being a critical part of that. And TAIT has definitely taken advantage of the technology improvements that the automation industry has taken to move a lot of things towards network-based communication as opposed to discrete wires. And so what's being shown here on this page is a very simplified system, but you can kind of get an idea of how it all connects together. We have two line colors here, an orange color, which is the Navigator network communication. So this is proprietary to TAIT, and is carrying the Navigator communication for queues and motion tasks across the network. And then we have the yellow line, which is that industrial automation field bus protocols. And with this being a backoff system, it happens to be EtherCAT. And so starting from the beginning, we need a way for this Epic console or our front end portable consoles, which is a compass unit, to connect into the system. So one of the things we need to consider is connection points. Again, TAIT has thought about this. We need it nearly in all applications. So we've developed a nav point. It's a stock product that we can pull off the shelf, make sure we include it in the bill of materials, and send it to the installation site to get mounted on a wall, and then the cabling run through the facility. That would connect again to that motion control rack, that MCR, that again is kind of the central hub of the system and does all the network distribution, but also is carrying the main core components of a system. Things like that ESA, that safety master. In this case, we're using an RS4, which again is just a stock product, but is carrying the task of both a PLC as well as our eStop master. And then we may decide that we need to link in some extra IO. So we're going to connect it with that field bus to some IO modules. And maybe that's bringing in extra eStop inputs, or maybe some hold to run inputs, a lift system perhaps, to make sure that we're getting our clears and things are able to move confidently to make sure that personnel are clear. We also have the ability to link in and distribute the IO outside into different racks or different enclosures. And then again, we get to that other big part of the system, the MCCs, where they're being connected via the Navigator network, where we're going to put another PLC to do the motion control. It's going to talk via field bus to the IO pieces, and it's going to talk via field bus to the drive itself to do the motor control. This is a lot better than having to run discrete wires for, here's the drive enable, here's the drive set point, here's the drive brake release. Like, the list could go on and on in terms of the number of IO signals you may need to a drive, or you just run a network cable and it talks via that. I keep harping on safety, and I think it is important in any automation system to ensure that things are safe and things are reliable, especially when it comes to the shutdown path or the eStop system. And so this is done with a combination of both networked IO, which is done via, or was being depicted by the yellow lines, and hard IO, because ultimately it comes down to usually a button or some kind of, again, limit switch that will need discrete wires run to it. And so again, similar components, we've shown a little bit extra here, that we want to have our limit stack on our machine. So that's being brought in via hard IO to some IO modules, which is then talking via the field bus to the PLC that's in the MCC, and that's being linked back to the safety master. So this could be limit switches on the machine, or in this case of the nav point, we have hard IO of the eStop button itself being brought into that IO located in the MCR and being forwarded then to the safety master. So what does this stuff look like? And how do we go about selecting it or sizing it? Again, Navigator was built from the ground up by TAIT. And we have a lot of insight knowledge into what it takes in terms of access count or safety processing to size our nodes. And what do I mean by sizing nodes? That's really processor power. So we have a couple different options when it comes to designing the system to make sure that we, one, have adequate CPU, but also when it comes to form factor. Not everything wants to fit in a 19-inch rack. Sometimes we want to build it on a panel. And this is, again, decisions that have to be made at the control system level, the control system design level, to ensure, we can fit the box in the physical space that has been either assigned to us or has been requested to us. Or in the case of touring, making sure that it can be swapped out quickly. So a lot of the touring equipment that TAIT provides is in rack mounts, because if they have a problem, they don't really have time to troubleshoot it. They're just going to pull the whole thing out and put a whole new spare in. Whereas with the permanent installation venues, they're really about longevity and ensuring, long run times for the shows or the venues. And so they want that discrete component level ability to swap things out or replace things to ensure that they can maintain that system for 10, 15, 20 years. I mentioned the nav points kind of in those simple risers. but this is what it kind of looks like in the rendering and how it might be operated or utilized. Where these are located, this is talking potentially with theater consultants, or we may provide the input necessary to where these nav points should be located. Certainly you want them at your operator position, but maybe you have a machine room that has all your winches in it. And so making sure that you have a way to, one, stop them if you were to be doing maintenance, but also maybe you want to plug in your maintenance pendant. So putting these in very strategic locations is part of the control system design that we look at to ensure that these are in locations that will allow for control of the system, but also good points of having spotters or anybody that's able to look at and see an issue when it comes to somebody not being where they're supposed to be and being in the way and able to hit that e-stop button, or anything else like that. So I talked about the maintenance console. So this is our compass. And so this would plug into one of those nav points in order to allow control. So maybe how many of these do we need in the system? That kind of falls to a combination between Ben and the technical business development team and the control system designers to ensure that the specification is being met, but also we're providing the functionality needed in the system to the end user. And then we, again, have our Epic console as kind of your main platform. The compass is really a handheld controller, maybe used to perform maintenance, where your Epic is your front of house console. It's really running the show and able to write cues, edit cues, provide that troubleshooting, as well as execute the cues. And then we have the platform itself, the GUI, the user interface. So this is not necessarily control system design, but something that is thought about quite in depth to make sure that the screens are well laid out and that the information presented is readable to the operator to, again, ensure that they can find issues quickly and get them solved, but also to ensure things are running appropriately and as they should, again, to foresee any kind of issues that may come up and flag it for maintenance. So Navigator is what? It's an operator, programmer, commissioning interface. It allows customizer interfaces. It does rules, cues, visualization, and monitoring. It's a real-time operating system, and we connect all these things together. And so what it comes down to with the control system design is really that Navigator and external devices. The commissioning and operation of a system, while is a consideration to control system design, is not our main focus, right? Our main focus is to ensure everything is connected and that it's connected to a level of thoroughness necessary to provide, again, the feature set that is necessary. So what are some of the things that we can connect and that a control system designer may need to be familiar with? Things like camera control and making sure that we get those networked into the system. Things like video displays and the different protocols that we can communicate with. If we have HVAC or atmospheric effects, things like pyrotechnics and fountains. Certainly in the theme park industry, we do a lot of interfacing with other shows outside of just motion control. And then systems like you'd find in a normal theater, either audio or lighting, making sure that those systems have the correct interface to the Navigator system is something that we need to consider to ensure that we're able to send the data that they need to either get triggered by Navigator or things with lighting, maybe being able to follow an axis or follow a lift through its motion profile. So then we've kind of talked about the system, we've talked about the components, we've talked about devices, we've talked about subsystems that we may need to interface with. And then it comes down to decision-making time and picking components. So what do we need to know? Or what questions do we need to ask? Voltage. Voltage is certainly one of those things. In North America, we have two main voltage classes, 200 volts, which we see as 208, and we have 400 volt class, which appears as 480 volts. And so this is going to determine what components you end up picking. Not everything can run from 200 volts to 500 volts. So you may have to change part numbers. You may have to change fuses, right? You can have more power watts in less current when it comes to a 480 volt system. So sizing fuses, sizing breakers is going to depend on whether we're running at 200 volts and it's 20 amps, or whether we're at 480 volts and it's 10 amps. Things like the number of axes. So again, I talked about the navigator nodes and not only their form factor, but their compute power. So every time we add an axis, we need to have a motion task looking at its I/O, looking at the encoder, doing the closed loop positioning of that, and sending that set point to the drive. So as we add more axes, we have more processing we need to do. We need bigger nodes. So that may come down to either just having the biggest node we can with the most CPU we have, or do we start looking at a distributed system and we start putting nodes around the building and segregating them to very specific tasks, be it an MCC has its own node, or maybe the grid gets a node and the fly loft gets a node, and then the basement or lift system gets a node. Talk about available space. So it can be great. You can take as much space as you want, but if it doesn't fit in the venue, in the building, it's not going to do the client much good. It's not going to be a very good design. So making sure that you are being aware of how much space something is going to occupy. And like I mentioned before, this kind of drives into that decision making when it comes to sharing a DC bus or doing those AC drives where they're all in one unit. Or do we have oodles of room? There's an entire machine room dedicated to things. And so making it to where it can be serviceable and looked after and maintained without having to, be a contortionist and get into a very tight space. Is this a new or is this an upgrade project? They have definitely different criteria. Obviously, with upgrades, you have to maintain usability of the system. So you may have to start breaking it out into different phases. Whereas a new system, you're essentially building it from the ground up. So you have a lot more things to consider. You need to make sure that you provide facility impacts to the electrical engineer to ensure that the switchboards are providing enough current for you. You need to talk with electrical contractors to make sure conduit is run or tray cable is run to be able to connect all these cabinets together. Versus an upgrade, usually everything's already there. And now you need to change the way you look at things and really focus on, okay, what is there currently and how can I reuse that? And again, if I'm taking something out that occupied a certain space, I probably have to put it in and occupy the same space. Our system architecture. So things like single axis versus multi-axis MCCs. Is this, do they not have the machine room? And so you have to put the MCC on the machine, or do they have the machine room and you can build big cabinets that are 10, 12, 15 axes of motion, and then it's all cabled out to the machine. Sensor requirements. Again, digital versus analog signals, safety versus standard I/O. One of the things that I didn't talk about in this presentation, which is definitely a big part of control system design, is analyzing hazards and mitigating risk. So people call it different things. TAIT, we kind of have centralized on a hazard analysis and a risk assessment. So this is how we define what needs to be safe versus what needs to be standard I/O. And you say, well, why can't everything be safe? Well, there's complexity involved in that and cost involved in that. And so we need to be familiar with what hazards are present and how we plan to mitigate them. And if they are planned to be mitigated by the control system, making sure that it is adequately reliable based on the risk or the hazard being presented, certainly when it comes to personnel. So I think we are just about at 15 minutes, which is perfect, hopefully, for our Q&A session. I haven't been monitoring the chat. I don't know, Rich.
Yeah, Adam, if I can jump in and speak to you, say, thank you very much. I want to just mention that Adam sprinted at a very narrow slice of what it is that this world of automation really is. And people spend years learning all of this stuff, and we learn on a continual basis as the technology changes, and we're ever gaining more and more information. So it is certainly hard to go and explain and explore every single piece of what a real automation system can be or is. So we take this all kind of with a grain of salt, that we're going to take a real quick sliver at this and run at it. And Adam, you did a fantastic job. So let's, if there are any questions, let's have them.
Yeah, definitely a lot of information thrown out. I didn't mention that I've been with TAIT for 9 years. It'll be 10 years next year. So there's definitely a lot of knowledge that has been absorbed. And so to try to regurgitate that in an hour means, yeah, we're running at light speed. So it's very fast, but I hope that it was definitely helpful for everybody that's attending. And again, opening it up to questions.
I think it was really great. Thank you both. So far, there are no questions in the chat. Oh, here we go. I've got two. We'll start with from Beth. What was your training, Adam?
So I went to, I guess I didn't say this. I'm based in Las Vegas. I came out to Las Vegas to attend University of Nevada, Las Vegas, UNLV, for an entertainment engineering and design degree. So that is my my secondary education, but I definitely was involved in theater in high school. So it really worked out to how my mind worked in terms of being very, math, physics, and technical based, and being able to merge it and apply it to technical theater. And that is definitely something that is hard to find in people in terms of both a strong theatrical background as well as the technical knowledge necessary. Obviously, I have done a lot of training with TAIT and over those 10 years. Definitely some of it is on the job training. And like I said, I worked in support, I did integration. So I've seen the problems that clients have faced, and I know what it takes to put this system together. So that has definitely provided a good basis and foundation for my understanding when it comes to doing control system design. And then TAIT has also, given us not only navigator training, but also industry training. So things like functional safety, going out and actually being trained by, TUV or TUV, who kind of is one of the third-party companies that looks at safety ratings on things, to provide us that. So engineering is, I guess, my background, but it was definitely geared into entertainment.
Awesome. Thanks for that, Adam. More questions are coming up, which is great. Shep has asked, this is a big one. So Ben and Adam, both of you, put your hats on here. You mentioned how recent advancements in automation technology have impacted entertainment controls. How do you think the field of entertainment control will evolve over the next decade or two? Ooh. So, what's it going to look like in 40 years?
So I'm happy to take that one, because as a member of the sales team, I kind of get a feel for what the clients are after. And I think a lot of where we go depends largely on what our clients demand. Obviously, the world of industrial controls will continue to get more and more robust, safer, more reliable, and as new communication protocols come up, we'll continue to get those into our system. But I think where we're really going is, as the world becomes more in tune with these more immersive experiences that we see popping up all over the world. It's not just people in the audience, people on stage, and we move stuff around them. There's these immersive experiences that happen to be coming up. And so I think where we are headed is this notion of show control and how we can deploy that from a holistic and immersive standpoint. And I like to use the phrase, not just show control, but really shared control. And so that all of these systems, lighting and audio and pyro and fountains, all of these can come into the same ecosystem of control. Because when you break it down, as all of these systems have become more sophisticated over the years, audio, lighting, they've all taken leaps and bounds in terms of technological advancements, and we can all talk together. And so now we're heading into this world where you can create these immersive experiences and everybody can queue and everybody knows where everybody is. And it's not necessarily reliant on a stage manager calling lighting Q1, auto Q1, audio Q1. We all know where we're all at and we can all queue off of each other. And this notion of shared control, show control is where I think we're really headed in the next decades. And it's really happening now, but we will get heavy into it.
Yeah, and I think one of the things that comes from that immersive aspect is certainly not necessarily automation technology, but more entertainment. And when I say entertainment, I actually mean like gaming technology, like VR and augmented reality are I think new players to live entertainment and the entertainment industry in terms of providing that additional step of immersion. And so that just adds another layer to it that needs to be controlled and queued. Certainly if you have just like, right, we've all seen projection mapping, but imagine projection mapping onto a moving element.
Yeah,
we continue.
Yeah, we continue to get deeper and deeper into the esports world. And it's huge. It's growing at an exponential rate, and they're continuing to come at us and finding where that integration of, gaming engines and Navigator and how we can explore those is really, it's exciting. It's exciting.
Absolutely. Ben and I have talked about this before. We share a vision that's where the entertainment industry is going. So I'm all excited. I get chills.
It's great. It's super great.
We continue to get more questions, which is great. I'm trying to decide how much time we have for two really interesting questions. So we've got about 7 minutes and 2 questions. I'll read them both and you can figure out how to answer them both. The first is from Sylvia, who says she's a mechanical engineering student with a theater technology minor. Do you have any sage advice for breaking into the industry? That's the first one. And the second one is, when you invite industrial control manufacturers reps to see what you're doing with their equipment, do their eyes always roll back in their head, or is it just the Rockwell guys? And then another one that just came in from Paul, what's the most challenging stage of the system design process? So pick which of those you want to answer in the 6 minutes we have left.
So let me answer the first one from a sage advice. I'll congratulate you on choosing the right pathway from a mechanical engineering standpoint with a minor in a theater. I personally, my background is a BFA in theater design and technology. I'm a theater guy, and arguably only through trials and tribulations did I end up working in the world of entertainment automation. I definitely had my ups and downs and cut my teeth, but that's a prime place to really be. Those are the people from a, frankly speaking, those are the people that we hire on a daily basis of mechanical engineers who can come and help us design theater entertainment equipment. But if you want to get more just general experience, I tell people this all the time, make sure that you are, pounding on the door at your local roadhouse, your local arena, go volunteer, beg, get paid, and go work load-ins, work strikes, do those work calls, because that's going to be where you really get your boots on the ground experience. And I can tell you, having worked for a lot of Cirque tours in the past, a number of those people, the really good overhire work that come in and help us load in. I mean, Cirque has a habit of hiring really, really good people right off of the show floor from the load in. So, go make sure you're doing your load-ins, load-outs at your local roadhouse and arena. Adam, you want to talk about Rockwell?
Yeah, so we don't use a lot of Rockwell. But I'll take it from the higher level of any industrial controls manufacturer or anybody that's in the industrial automation sector. And that, yeah, when we bring them by, they're usually, you're doing what with our equipment? Especially when we start flying people around or we start, moving giant stages around. So usually they're pretty excited about it because it's also different to them. They're like, oh, this isn't just a factory making trinkets. Widgets. Yeah. So they're usually pretty excited about it. And sometimes, I mean, they're usually pretty good. I don't have a lot of experience with the Rockwell guys. And then the most challenging stage. So I'll second everything that Ben said about getting into the industry. Like, don't sweeping a floor is not past anybody. If that makes your network, if that gets you your foot in the door to make a connection to get a job, do it. And then challenging stage of a control system design process. The most stressful part, I guess, is the timeline. I usually focus in fixed installations, which are like year-long projects. I'm dealing with a fixed installation that seems to be wanting to happen on a touring timeline. So that's definitely the most stressful thing right now. And with obviously recent global events, procurement and lead times are, while it's not directly impacting how we design enclosures, it adds a whole extra layer of, well, I can't get that in a timely manner. What can I substitute it to that still carries the technical characteristics that I need, be it a breaker, again, a PLC card, in that I can get. And when we start getting into the field bus and like the specific manufacturers, I can't go pull a Rockwell IO card and slap it on a Beckhoff PLC rail. Like, I'm kind of limited in certain things. So that has definitely been a challenge that I really didn't have the same experience of before the pandemic and the logistics chains that we are currently facing.
I imagine that doesn't often come up in any of the coursework that might prepare somebody for this, a global pandemic impacting the worldwide global supply chain for name a part, right?
Yep.
Yeah.
Mary, you look like you were about to ask a question. Did you?
No, I was just listening intently.
Oh, okay. Well, we are just about at time. It doesn't look like there are any more questions in the chat. Ben and Adam, thank you so much for joining us today. This was great. So much information. It was a very steep climb and one that was really exciting. We went from basically like AC power to high level conversations about networking and connecting devices, which was fantastic. So thank you both for your time. Thank you everybody for joining us. And we will see you all again next month, where we look to have Ed Weingart, who is the new co-director of the Krennecke Arts and Engineering Institute at the University of Connecticut, join us. So watch for information about that. Thanks, everybody, and we will see you all next time.
Thank you.
Thank you.
Thanks all.